guys were trying to put everything together in a sketch. So first of all, help me out. What pre-cal stuff do we know? Because those are the easy things that we can just like plot really quickly, right? So what's some pre-cal stuff we know? Intercepts? Which ones? 0, 0, and 4, 0, right? 1, 2, 3, and 4. Cool. Any vertical asymptotes? Oh, no. Any holes? No. Any other asymptotes? No. There was nothing else pre-cal, huh? All right, fine. Calculus. What do we know? Hey, don't we have 1, 2, 3 more points? Well, kind of. Where's 1 going to be at? 27. Up here somewhere, right? Okay, there's 127. Where's 2 going to be at? Negative 16-ish. Okay, so we'll say this one's negative 16. We'll say this one's 27-ish. What's going on at this one? It's uh-oh, hold on. Is it negative 27? We plugged it in quickly yesterday. It's negative? Does that make more sense? I can double check. I have the function in my calculator really fast. I think you guys are trying to help me out, and I might have just not written down the negative at the end, so you're going quick. Oops, that's not what I want. Where is it at? 4? No, 1. Yeah, it's negative 27. Okay. Why does it make a lot more sense? What's supposed to be at the 27? Or at the negative 27? A minimum. Oh, that should be like down lower, right? Okay, there we go. So that's going to be a min. That's a point of inflection. Anything else? I guess not. So we know that the function is supposed to decrease all the way down to the min. It's a really squished function. Decrease all the way down to the min. Then at 1, it's supposed to start increasing. And then at 4, it keeps increasing. So we have concave up. Then between 2 and 4, concave down. That's a little rough to do. So it's concave up all the way until the point of inflection at 2, then it's concave down, and then what happens? After 4. Then concave up. Nice. How you guys got close? About 5? Okay. How many guys got like half the clues? Okay. Add another 5 or 10. Does that make sense how I put it all together though? I got my important points. I knew there were no vertical asymptotes or anything else or holes. I decreased, just like my sign chart said, decreased until x equals 1. I increased, technically, then forever on after that, but I had to also make sure concave up all the way to 2, then I had to go concave down all the way to 4, then concave up afterwards. I think without calculus, we would have really messed that one up if we were just in pre-cal. Now, one last one. Go ahead and write down the function and write down the derivative real quick. Let me go and zoom in. Sorry, single page. How is he back there? I have no idea. There he is. Go ahead and get down those derivatives. And homework is technically your choice. Could you start with the pre-cal stuff on those first 5 homework problems? Yeah, you could start with pre-cal, then find derivatives, then do calculus. You could technically do what I've said about the reference guide and not do all the nasty derivative work on your actual homework if you like it being nice and pretty. You could do all your derivatives for those first 5 homework problems on one page, first and second derivatives, nice and simplified. Then use them on another page as you do your actual homework. But I need to see derivative work. It's only the first 5. Bridget? Just for these ones, because these ones, the directions say, basically, we want everything you know about this function, including increasing, decreasing, and concavity, second. So we have to. So remember, 3.5 is the big summary of bringing everything together. All right, so we have our 2 derivatives. I'll be back in just a second, but let's go ahead and do some pre-cal stuff, yeah? So, x-intercept, what do we do? Yeah, set y equal to 0. When is y going to equal 0? When each... Yeah, when each one equals 0, right? So that's going to happen at 0, 0, and 4, 0. You guys got it? 0, 0, 4, 0. Y-intercept. Oh, plug in 0. But 0 times 4 minus, that's 0, right? Vertical asymptote. Is there a denominator? Nope, so none. Holes. Is there a denominator? Nope, so none. Horizontal asymptote. Now guys, in your homework, if there's a none, you don't technically have to write it. You can. Just show me that you're going through each of the steps. But if there's a none, you can go ahead and just be like, well, I'm not going to write them because he doesn't really apply. If that helps and saves a little bit of time. Okay? Horizontal asymptote. Nope. Why? No denominator. If there was, we'd do degree tests. Some of you guys had to struggle with oblique. I think at least, was it just one? My ones who got through all 5, just one has an oblique? Okay. Remember, you only have to worry about who's an OA, an oblique asymptote, a slanted one. When the top degree is how much higher than the bottom degree? Just one. And when you do that, you plug the F, the top, into the box. You do a long division. You're going to end up with some sort of linear mx plus b as the answer. Whatever remainder have, you ignore. We went over that in class. We wrote it down in the clues in our notes. Some of you might just need to kind of grapple with that when you get to the 1 with an oblique. But long division. Symmetry. Plug in a negative x and ask yourself what's going on. Oh, hey, it flips the sign of that one. Okay, that's good. So it looks odd, except, what's going to go on the inside, guys? Oh. It flips the sign of everybody because it makes everything negative, but doesn't it also flip the sign of the inside? The sign of the inside? It flips 1, it doesn't flip the 4, so therefore this is going to have no symmetry. It flipped 1, it flipped the other, but it couldn't flip the 4. That's going to be a none. And domain? Ooh. Not all real numbers. What do I have in my function? Square root. And remember, what's under the square root has to be positive. Greater than or equal to 0. So I have to set that greater than or equal to 0. If I move the x around, my domain ends up being x must be less than or equal to 4. Okay, well, we got a few pre-calc clues, not a lot though. Hopefully we get more from calculus. Okay? So then, as we go to calculus, critical numbers, set the top equal to 0 and the bottom equal to 0, right? At x equals 8/3, and then x equals 4. Technically, why am I crossing off 4? He's the domain, so we're already going to cut it at 4. Wait, cut it? Oh yeah, with our sign chart. Uh-oh, hold on now. Doesn't x have to be less than or equal to 4? Can't go greater than 4, otherwise my function, my original function, doesn't exist. 8/3, I'm still going to put that because that's only 2 2/3, which is going to be less. So 8/3. Increasing, decreasing, we plug into the first derivative, right? Just for sake of illustration, you guys, once again, the same way you didn't need to watch me find derivatives, you also don't need to watch me. There we go. You also don't need to watch me plugging in for signs, right? So, when we plug in, we're going to end up with a positive and then a negative, so increasing and then decreasing. Do we have any relative extrema? Do you see it? What is it? Yeah, we have a relative max at, now remember, our homework already kind of modeled it for us. We're going to actually find the points of the maximums and minimums. Well, this one doesn't have them in. But we're going to find the points of the extrema and the points of inflection because we want to put it in a graph. And to put it in a graph, we need an x and a y. So we're just going to plug and shove our 8/3. Once again, I said if you want to save a little bit of time and plug and shove in the calculator, that's okay. Math fraction, got it. It's a nasty decimal, so we're going to leave it.
Just simplify the decimal.
Yeah, I'll just simplify the decimal. 3.079. Feel bad putting a decimal if it's technically a non-calculator, but we need to be able to know where to put it, right? So we'll put it around 3-ish. Pips, we set the second derivative equal to 0, and we end up with, remember top and bottom, x is going to equal on top 16 thirds. And then 4. 4 we're going to ignore, but question. Here's where it gets weird. Why am I going to put an X through 16 thirds? Yeah. Who is 16 thirds? 4 and, no, 5 and, right? 5 and 1/3? What's my domain? Oh, well, forget that. He can't even fit. Really? This is going to happen in homework. What if you have no legal points of inflection? You make a little sign chart and you say, I guess I only have to test one time. If there's no point of inflection, or I should say if there's no pit, if there's no possible inflection point, all we have to do is plug in 1. Plug in 1 value. I don't know, what looks good? 0? That looks easy, right? So plugging in 0, we end up with a negative number, which means concave down. Are there any points of inflection? No. Concavity is not changing.
0. Oh.
I just plugged in 0.
Second derivative.
Yeah, plug in the second derivative. I'm going to go ahead and go dual page it, and we'll see if we can put this one all together. He's kind of funny in a way, but in a way he's kind of an easy graph. Kiddos, what pre-cal stuff do we know? Any intercepts? Which ones? 0, 0, and? Okay. Domain is less than or equal to 4, so I'm not going to even have to go any higher. I have to end at this one right here. I have to end at 4, 0. So that's all the pre-calc. What does calculus tell me? Ooh, I have a point. 8 thirds, which is 2 and 2/3, there-ish, and then 1, 2, 3-ish. So 2 and 2/3-ish and 3-ish. That's my relative max, right? And it's concave down, that makes sense, it's a relative max. And all I know is somehow it's increasing, and then what does it do? Decrease, and then it stops. That's it. Check it. Concave down? Yes. Increasing, then decreasing? Yep. Relative max at 8 thirds, 3.079, yes. Now, hold on, we just did that whole example in, oh my goodness, like 5 minutes? So what makes this so hard? What I give you?
Finding the derivative.
I gave you the derivatives, right? Okay. So, for numbers 1 through 5, you have to find the derivatives, and you have to do them carefully. But here's what I'm going to do. I'm going to go ahead, we shouldn't do this, but I will. I'm going to go ahead and find the derivatives myself. I'm not going to do all 14 identifiers. I'm going to find the derivatives myself for the first 5, my way. Okay. I'm going to go ahead and post that online in your shared folder. You guys have like a folder called assignments or something, right? I think you do. And I think in there there's like a little keys, a key folder. So I'll go ahead and make it homework number 21, 14 identifies derivatives key. So that way, when you guys are finding your derivatives, if they're not matching up, you can go compare your work to my work. Sound good? Because I know not all of you can come in. Now there is 0 period in the morning if you're still not able to find mistakes, or if you're not able to put all the stuff together, or in some of the concept-y problems past the 14 identifiers. But I know derivatives can be hard. And so to try to alleviate some of the questions on, my derivative isn't working, let me go ahead and post that work for you, because I know people who were working on it yesterday, that could have been helpful. And so, since all of you can't sit down and do derivatives with me, I'll go ahead and post that. Sound good? Where's it going to be again? Yeah, our shared folder where like everything is underneath assignments, and I think there's like a keys, like an answer key one. All right, kiddos, we got to do some concept-y ones, because remember, the first 5 of homework, that's the bulk of homework, or 14 identifies, but then it goes into some concept-y stuff. That's going to help us with the test coming, with AP practice that we're going to be doing on your practice test, etc. All right, here we go. This is from section 3.5. The graph of the first derivative, the graph of who? Okay, this is the derivative graph. Remember in your cards, it'd be the derivative one, not the function one, right? The graph of the first derivative of a function, f, on the interval -7 to 5 is shown. Use the graph to answer each question. Now, I'm going to do shortcuts as I talk about each question, but couldn't we take him and couldn't we make a quick little sign chart of where he might have come from? for instance, hold on, gotta think about this. In a sign chart, don't we put the zeros or the DNEs of the first derivative? Okay, now hold on. First of all, my number line shouldn't go on forever, right? Technically, it should just go till -7 and 5, right? Okay, because it's cut off at endpoints. Question. Approximately, what are the zeros of this graph? See it? Zeros of the derivatives, -3 and 1. That's who I'm plugging in as my critical numbers. Not the horizontal tangents, that would be if this was f. This is f prime, so I'm using his zeros. Okay. Now, how do I fill in the signs looking at this graph? Am I asking myself to fill in the signs of the derivative? Am I asking myself above, below, or increasing, decreasing, and they are very, very different. Positive, negative, which means
Increasing, decreasing on the left.
he's going to be increasing, decreasing, but I'm not looking at him. Who am I looking at? So I just want to know positive or negative. And do you remember? F prime is positive. This graph is positive for y values that are above. And this graph is negative for y values that are below. So I'm just asking myself above or below for the signs. So question, in this interval, above or below? The derivative is positive because the y values are positive for f prime. So then, right here, above or below? Above or below? Perfect. It's contrary to what you're naturally going to go to, which is why we have to somehow break this down, because you're going to say, it's decreasing, but you're not going to think f prime is decreasing. You're going to answer this whole where is f decreasing using where f prime is decreasing, and you're not doing it at the same places or for the same axis. But looking at the sign chart, well, question, kiddos, how would you now answer letter A? -3 to 1, which is weird on f prime, but f prime is below for that interval, so f prime is negative for that interval. The sign chart helps us probably more than the graph does, but we have to make it. So decreasing for x within -3 to -1. Positive 1, sorry. Don't worry, you're going to use practice a little bit in homework. And there are plenty of odds that you can check with CalcAB, etc. Not plenty, because I'm going to, but. Letter B. We're going to do some more practice on this. But the question is, on what interval is the graph of f concave down? Huh? It's concave up. Don't use it. Who's concave up? F prime, not f. We're not looking at f, so we have to think about it. Now, guys, from the increasing, decreasing sign chart, could you kind of guess where f is concave down? Where would you guess f is concave down? Uh-oh. There's a point of inflection somewhere, right? You would guess negative. Okay, so hold on. How do we think about, we kind of see the concave down. We're just not exactly sure where to end it. We're pretty sure that we can say x is within -7 to...
-2.
Okay, but how do you know for sure?
The f prime graph's decreasing.
Another way of looking at concavity is to ask yourself, what is f prime doing? F is going to be concave down when f prime is decreasing. Let me get the whole page so you can see it. So if we were to make a second derivative sign chart, and some of you, this is the easiest way, is to pull yourself out of this graph because he's too confusing. I'm going to quickly cheat just a little bit. We don't usually write this middle one, but on this type of example, it's super helpful. Question. In a second derivative sign chart, we're asking for the zeros of the second derivative. Well, how do we know that? The second derivative is the derivative of the first derivative, meaning he's the slopes of this guy. We already have the first derivative. The first derivative slopes is the second derivative. So we need to ask ourselves the question, where does f prime have a slope of 0? It looks like at 1. And then we have to ask ourselves, okay, what are the signs of all of the slopes from -7 to 1? Negative. That's going to be the sign of the second derivative. And what are the signs of all of the slopes after 1, before 5? Positive. Or you can think f prime is decreasing, because they mean the same thing. F prime is decreasing from -7 to 1 and increasing after. And what does the negative positive of the slopes of the derivative or the decreasing increasing of the derivative itself point to? F being concave down or concave up. Katrina. Thank you.
Yes, yeah.
Yeah, I didn't throw them in. Okay, so how do we answer the question now? Where, for sure, do we stop this concave down interval? -7 to -1. Now, here's something that's going to be a little tricky. Why technically, even though for concavity increasing, decreasing, we've been consistently keeping them open, why technically should that be closed? What's going on at -7? The slope is down. The slope is negative at -7. Usually we're cutting it off at zeros or DMEs, so we don't include those in our intervals. But since they cut off at -7, -7 has a negative derivative. -7 at -7 is in the midst of a concave down piece. Now, to be honest, I haven't really seen or heard of AP guys taking off for that little closed bracket, but technically I didn't want to give you the wrong answer. So we do keep it open at -1 because that's a 0. That doesn't count as positive or negative, it's just nobody. But at -7, the slope is, the tangent line is negative, so we have to exclude them. Letter C, at what x value does f have a relative extrema? Well, that'd be so hard because it's not -1. We're asking about f, not f prime, except, don't we have a sign chart?
Yes.
Sweet, what does the sign chart tell us?
Relative extreme.
Relative extrema. What do we have at -3?
Relative extreme.
Because we've already done the work. What do we have at 1? Now the crazy thing is, do you see that really clearly in the graph? Most of us would probably have to say, yeah, no. But what's going on?
Tangent line is there.
At each of these, the tangent line is 0. These are critical numbers. And the derivative is changing from positive to negative. So the function is changing from increasing to decreasing. That's a maximum. And the derivative is changing from negative to positive. Function is changing from decreasing to increasing relative minimum. We have to pull ourselves out of this graph. We're not looking for f prime's min. We're looking for f's relative extrema, which means we have to think about where this graph changes from above to below and how it changes. Positive to negative, that's a max. Negative to positive, that's a min. But if we do the sign chart, we can see it. And it makes it a lot easier on our brains. Last one. When does f have a point of inflection?
Changing.
When the concavity of f changes, which means the slopes of f prime change signs. Now, if we look at the second derivative sign chart, it's easy. Where's our point of inflection? We're not putting any y values because we don't even know who the y function is. They didn't give it to us. Probably something cubic, not quadratic, but either way. At -1 is our point of inflection because the signs change, but on the graph, the second derivative is seen as the slopes. So whenever you have a first derivative graph, f double prime is seen as the slopes. And that's how we visualize the second derivative graph. Alright, cool kids. That was a little rough. But how we do? We're still alive? Okay. Can I go ahead and, just because this is a big idea, can I get you another sample problem from this? And let's see how we do. Okay. It's up to you how much work you show. You're allowed to collaborate in your groups. But I want you to take this graph of who? Okay, so we're not looking at maxes and mins of him, right? We have to use him to help us think about f. This is the graph of f prime. Can you figure out where any relative extrema, any relative mins occur, if any? Where any relative maxes occur, if any? And where any inflection points occur, if any? Again, I'm going to go ahead and make this a little more accurate. Hold on. Alright, let's see what you can do. If you want to make a sign chart like we just did, you can. You have to use the same technique.
Well, you're supposed to look at the slope. So 0 from the base so that means it'll be positive.
You see that it's a negative
Okay, you guys ready? Here we go. I'm just going to give answers and I'm going to show work. Let's see if you got it. Alright, hold on. Eyes up here, eyes up here, eyes up here. Hold on. Okay. Ready? I'm going to show it just kind of quick. Nothing's going on at -1. At least not relative min and max wise. This one, negative to positive, decreasing to increasing. There's a relative min at 1. And there's a relative max, positive to negative, at this increasing to decreasing, at 5. Now pause, if you didn't get those two right, you were looking at the graph wrong, and that's okay. That's one of the hugest, most common mistakes that calculus kids as far as visualizing these make. Why did I not say 0? I don't want f primes, man. What do I want? F's, man. So I cannot choose what I see. I cannot choose what I see. If you did make a sign chart, hopefully you made something similar to, do you put in -1, 1, and 5 as your critical numbers? The zeros. Then did you figure out for f prime, below, below, above, below? And so then you got your decreasing, decreasing, increasing, decreasing. You got your min at 1 and your max at 5. You got it? Okay. Then, without any further ado, question. Did you get your points of inflection to be -1, 0, and 3?
Yeah.
Why? Where are the slopes changing signs? At each of these. The slopes change signs. Remember, the slopes of f prime indicate f double prime. And if the slopes change sign, or if f prime changes from increasing to decreasing, hey, a concavity change occurred in f. So wherever f prime changes from increasing to decreasing, or you could say f double prime changes from a positive to a negative slope. At -1 is 1. F prime changes from decreasing to increasing, there's a change at 0. Or the slopes change from negative to positive at 0. And last but not least, there's another change at approximately 3. Does that make sense? So then, if we were to do a second derivative sign chart, we would have done, where are the zeros? -1, 0, and remember horizontal tangents. And we would have had a positive slope, aka f double prime positive, a negative slope, a positive slope, a negative slope. There were changes at each of those. Technically, remember f prime is increasing, decreasing, increasing, decreasing, which shows f is concave up, concave down, concave up. If you wanted to show the sign chart. Katrina.
For the sign chart for f double prime, is that when you actually look at the graph at random?
You look at the graph, but you have to still stay oriented with and looking at the zeros or DNEs of the slope. So with the second derivative, you're allowed to look at the graph because you're looking at the graph's slopes for f double prime. Does that make sense? So the pips will be the zeros of the second derivative, or DNEs, which are the zeros or the DNEs of it. And so in a sense, you can say all of the relative mins and maxes of the first derivative should also be points of inflection of f. Does that make sense? Now, let me show you one other spiffy thing. Since we did all this work with looking at the graph of a derivative, we can find from the graph of a derivative where relative extrema occur and where points of inflection occur. So I want you guys to go ahead and look at, I think you have something in this section. Maybe it's 38. I don't remember. I gave you one in here. We're going to do one example. This is another concept you want, and you're like, oh no. They want us to find all this stuff, so we're going to have to do 14 identifies, right? What do they say we're allowed to use? Now they say computer, algebra system, blah, blah, blah. It's a graphing calculator, right? Okay. So question, what's going to be really easy? I have it in my graphing calculator. What's going to be really easy to find for this function if I'm using my grapher? The graph, and what do they want specifically? Okay, so relative extrema, that's easy, right? We graph it, and we say da-da-da-da-da-da-da, okay, that's great, I need a zoom standard probably. We might have to play with our window, right? Pre-cal stuff. Maybe zoom standard. Oh, well, that's a nice picture. Okay, question, couldn't we use second trace, max or min, in order to help us find what we need?
Yes.
Okay, so max and min isn't going to be bad. Let's see if I can go, remember you have to go to the left of the min, to the right of the min. I'm just going to indicate real quick. Alright, there's a min. So that's easy, because we're looking at the graph of f, so we can look at his min. Okay. Can I find a max at the same time? Now here's a problem. Question. How can I find the points of inflection? What feature can I use where I don't just have to eyeball? I need to find a point of inflection. What feature can I use? Is there a function that allows me to find point of inflection in that nice trace menu?
Yes.
Well, let's check it out. Yeah, you guys are all looking now like, uh-oh, hold on. If we're allowed to use our calculator, we really want to use it, right? But question, is there a point of inflection feature? Aww. So we can't use our calculator to find the points of inflection?
Yes, we can.
Yes, we can. Yes, we can. We just can't use the original function graph to find the points of inflection. What else could we do? We could go ahead and find f prime. Stick with me. Hold on. I want to graph the derivative. For points of inflection, I want to graph the derivative. So then if I go ahead and, okay, quotient really fast, bottom d top, which is going to be 20x squared plus 20, minus top d bottom, which is going to be 2x times 20x, which is going to be 40x, right? All over bottom squared. Minus plus 1 over x squared. You don't even have to simplify.
It's 4x squared. That's 2x times 5.
Oh, thank you. Thanks, Lloyd. I'm doing mental math too fast. If I was to throw this graph in, okay, let's get rid of this. I'm not even simplifying, whatever, my graphing calculator can do the work, although it'd be probably faster if I did simplify it. You guys know I'm using my pretty little fraction you do. I'm going to prove a point. We're literally just going to leave it the same, even though I could do 20x squared minus 40x squared to be negative 20x squared, but either way. Minus 40x squared all over x squared. Why am I graphing the derivative? To find points of inflection. And for this graph, it doesn't make a huge difference, but for some on the AP, it would be near impossible to try to figure it out just eyeballing a graph. But if you graph the derivative, all of a sudden, what are we looking for in the derivative for a point of inflection? We're looking for changes in decreasing to increasing, increasing to decreasing, decreasing to increasing. Oh my goodness, we're trying to look at his relative extrema, right? So then if I was to make my y's a little bit bigger, because I can't see everybody right now. I'm just guessing. Oh my goodness, he has to go higher? This is crazy. Wait a minute, what's going on at 0? There's a vertical asymptote. Did you guys even see it? I didn't. Not when I was looking really carefully. There's a vertical asymptote. So hold on, when they're asking us for vertical asymptotes, we have our max, we have our min. This is our graph of our first derivative. There's a vertical asymptote, first of all, at x equals 0. So forget him. He can't be an answer. So I should stop looking because I'm going to go forever. The question, wait. Can I find points that mark by finding relative mins of f prime? Can I find my points of inflection? Yeah. All right, cool kids. You know what to do. Yeah, we do the question. Talk about questions we have on the concepts and stuff. Tomorrow is our practice day. Tomorrow is our practice AP review. Oh! Brandon, if you're here, give us a comment. Angela, you're left. Bridget. Trevor. Jason. How do you like one of the questions?
They're all complete, they're not like all